All right, everybody, we're back again. And in this video, we're going to talk about material from Section 5 of Unit 4 of AP Calculus, solving related rates problems. So in this sequence of videos for this section, we're going to talk about strategies for solving related rates problems, and we're going to work our way through a couple of examples, setting them up, walking through the steps, and seeing how this is all done. Okay. Related rates, as we mentioned in the previous section, involve how different quantities vary with respect to time. And this is a six-step strategy process that I've been telling my students to use for years at this point. So let's take a look and see what we've got. First, draw a picture. Name all the variables and the constants. Use t for time. Assume all the variables are differentiable functions of t. Write down the numerical information that you're given in terms of the symbols you've chosen. Write down what you're asked to find, usually going to be a rate, expressed as a derivative. Write an equation that relates the variables. You may, and it says here in parentheses, usually you will. I've found that a lot of times we do have to combine two or more equations to get a single equation that relates the variable whose rate we want to the variables whose rates we know. That is always a possibility. Notice this bolded capital thing here. This is kind of important. Do not substitute non-constant numerical values before differentiating. So for instance, if I'm talking about a numerical value and it's something that varies with respect to time, that's something that I need to wait until after I've differentiated before it goes into my equation. Then we're going to differentiate with respect to t, which will allow us to express the rate we want in terms of the rate and variables whose values we know, and then we're going to evaluate. Use the known values to find the unknown rate. Let's work our way through example 1, using these 6 steps. Example 1, a tanker is spilling oil into the water, resulting in an oil slick that is close to circular. And so we're going to treat it like it is circular. At the time that the slick's diameter is growing at the rate of 8 feet per second, the diameter is 250 feet. At what rate is the area of the oil slick increasing? So from a picture standpoint here, we've got a circular-shaped oil slick. So I'm just going to draw a circular-shaped region here. And it talks about the diameter a couple of times in the problem. So I'm going to label the diameter of this in here, and I'm going to use capital D to represent the diameter. I might also, something that we use a lot with circles, we might also, talk about the radius. And of course, the area of the whole thing is A, my area. So those are the variables that we have in this particular problem. We don't have anything that's constant. The diameter and the area of the circle are changing as time changes. So we don't have any constants in this particular picture. Then we're supposed to write down the numerical information in terms of the symbols that we've chosen. So let's see. The diameter is 250 feet, and at that moment in time, the diameter is growing at the rate of 8 feet per second. So the rate at which the diameter is growing, that's going to be dd dt is 8 feet per second, and d is equal to 250 feet. And one last piece of information that I'm going to write here. I'm going to write down what I'm being asked to find. We're trying to find the rate at which the area of the oil slick is increasing. So what are we looking for? We're looking for dA dt. Okay. So let's look at what we've got going on here in this situation, because now we're going to try and write an equation that relates the variables appropriately. We know dd dt, and we know the diameter, and we're looking for dA dt. So we want a formula that relates the area and the diameter of this circle. Now, the most common formula people know for the area of a circle is, of course, that the area is equal to pi r squared. But that doesn't have the diameter in it, so we need to get the diameter into this equation. And in order to do that, we're going to use the relationship that exists between the radius and the diameter of a circle. The radius of a circle is equal to 1/2 of the diameter. And so substituting that into this equation, I can create an equation that relates exactly the two variables that we need to have related in this particular situation. The variable that we're looking for is related to A, and then we know d dt and d, so we've got d in here. Now that we have this equation that relates the variables, notice I'm not going to substitute 250 in here for d, because 250 feet is a snapshot. It's what the diameter is at a moment. The diameter is changing. The diameter is not a constant value. So I'm not going to substitute that into this equation before I differentiate. So now we're done with step 4. Now we're going to differentiate this with respect to time. So I've got dA dt is equal to pi over 4 times 2d dd dt. And so simplifying that, we get dA dt is equal to pi over 2 d dd dt. Okay. And now I'm going to go ahead, now that I have the equation for dA dt, I'm going to evaluate. I'm going to substitute. We're looking for dA dt, so we'll leave that by itself. We know what d is, it's 250 feet, and we know what dd dt is, it's 8 feet per second. And we multiply all this stuff out, and we end up with dA dt is equal to 1,000 pi, and we need units. And there's two different ways we can come up with the units here. We can use our common sense, or we can actually include the units in the calculation when we do this. Common sense, area of a circle in this context is measured in square feet, since the diameter is in feet. So dA is in square feet, and the time unit is per second. So that's going to be my unit for this area, the change of area. One other way that I could have done that is, if I look at this, 250 is measured in feet, pi over 2 doesn't have any units, and this 8 is measured in feet per second, and so this is feet times feet per second, and if we do the arithmetic on that, we end up back at this unit right here. And for those of you who love the decimals, you could rewrite this as a decimal, and it's going to be dA dt is equal to either 3,141.592 or 3,141.593 are also acceptable answers here if you wanted to convert them over to decimals, but I think I would have just left it as 1,000 pi. All right, you know what? That's where we're going to call it quits on this video. We'll come back next time and look at a couple of more examples of related rates problems, and we'll see you then. Have a great rest of your day and enjoy yourself. Have a good one.